Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson, we talked about another application of Ohm's law, and of course it was the capacitor circuit. And what did we do in that circuit? Of course, we connected the capacitor solely, let's say, with alternating source. And of course, we do know that the capacitor, you can say it stores electrical charges, or you can say it stores electrical charges in general. One of the plates store, let's say, positive charges. The other plate would store electric or negative charges, to be more specific, yeah? And of course, after that, we said, but remember, once we connect an ammeter, let's say, with the circuit, of course, that is connected to the capacitor, and of course, a voltmeter across the capacitor, we will see that the reading of the ammeter would reach maximum while the voltmeter is still reading 0, and then we will see that then the reading on the ammeter is, let's say, decreases gradually while the reading on the voltmeter increases gradually until the reading of the voltmeter becomes maximum, and then for the ammeter becomes, let's say, minimum or 0. And of course, we learned that, or we said that, the voltage lags behind the current in a capacitor circuit if it is only connected to the circuit, or only capacitor connected to the circuit by an angle of 90 degrees, you can say, or pi/2 radian, you can say. So of course, and then this is basically the circuit, and this is basically for, let's say, the sine graph, or you can say for the current and for the voltage. As you can see here, you can see that when let's say the current is maximum, as you can tell from this point, the reading on the voltmeter is 0, or you can say minimum, while this one becomes maximum, this one becomes minimum, and all that. And of course, we said if we draw the phase difference or phase angle difference between the two, we would see that the current would be leading the voltage by 90 degrees, or you can say the voltage would lag behind the current by negative pi/2, or just 90 degrees. And of course, we said for the instantaneous values or equations, we can write it either current or instantaneous current equal to I maximum sine omega t for the voltage, because this one is, we don't say this one is leading, of course, so we'll have to write negative pi/2 for the voltage, knowing or representing or indicating that the voltage lags behind the current by pi/2 or 90 degrees, you can say. And if we don't write it this way, of course, we can write it this way. We can say the instantaneous current, this omega t plus, of course, pi/2, indicating that the current leads the voltage by 90 degrees here. So we can say the current leads the voltage by 90 degrees, or we can say the voltage lags behind the current by 90 degrees as well. And of course, we had capacitive impedance, just like, for example, the resistance, and of course, inductive impedance here. We have capacitive impedance, the resistance that is, let's say, provided by the capacitor, and of course, it's called capacitive impedance. We said it is the ratio of maximum voltage to the maximum current. That is one way to say. If not, we can say it is the opposition provided, or capacitor's opposition to the alternating current. That is another way if we want to define XC, or capacitive impedance. And of course, we said there are multiple ways to find this, yeah? But remember this, guys, if you're going to use this one here, using Ohm's law, of course, we'll say capacitive impedance equal to V maximum over, let's say, current maximum. By the way, you can use these values, either maximum over maximum, or effective over effective, or instantaneous over instantaneous. You cannot use maximum with effective simultaneously or together. No, it has to be maximum, maximum, or effective, effective, or let's say instantaneous with instantaneous as well. And of course, there is another way to find that opposition. That is, of course, it is omega c, you can say, or x equals to 1 over omega c. That is another way to find that. And if you do remember, we said for the capacitive impedance, it did depend on the frequency of the circuit and was directly proportional. But as you can tell here, it is inversely proportional with the capacitive impedance. As you can see, it is 1 over omega c. You do know that omega is equal to 2 pi f. So if we substitute this value into this, this is where we get xc equals to 1 over omega, or you can say, by the way, this has to be 2 pi, or you can say that is 2 pi f c here, okay? Instead of saying omega, of course, we'll have to say 1 over 2, that is the frequency, then multiplied by the capacitance, or the value for the capacitance here. Okay, and then moving on to this, and obviously, of course, we did talk about the units for this. We said since the unit for capacitor is, or capacitance is measured in farad, so if we go back to this one here, of course, you can see that this one here, that is measured in ohm, this is measured in, you can say hertz, and of course this is farad. If we take the farad there, the farad equals to 1 over the unit for frequency is hertz, and of course the unit for resistance that is becoming ohm, you can say. And where do we get this one from? We got it from here, or you can see this as well. By the way, we get all this from the main equation. You can just let's say manipulate the equation, or let's say you can rearrange, will be the more proper word to use here. If you rearrange the equation, this is when you get. And of course, don't forget we have another equation which is specific for capacitor, or you can say the one for capacitor, capacitance, or the capacitance of a capacitor equals to the charge divided by the voltage. And of course, we did talk about this one. We said, what does XC depends on? The capacitive impedance. It depends on two things, yeah? It depends on the frequency, of course, of the alternating circuit or the source, you can say, which is inversely proportional. Remember this, which is inversely proportional with the capacitive impedance, and also it depends on the capacity of the capacitance as well, okay? Or capacitance of the capacitor, which is also again inversely proportional. So also remember this, we talked about this tip as well. We said whenever capacitance is given, always find XC, because like 99% of the times you're going to need XC as long as the C, or the value of a capacitance is the value of a capacitor is given. Okay, so and of course we did went through this one as well. How does the impedance of a capacitor in AC circuit varies with the frequency? We said it varies inversely. Why? Because we said that omega C equals to what? We said omega C equals to not omega C, X equals to 1 over omega C, yeah? So of course you can see that 1 over 2 pi f multiplied by the value of the capacitor. So you can see here, how does it vary with the frequency? It is inversely proportional with this. By increasing the frequency, the XC will decrease and vice versa. Now let's begin the new lesson at this point right here. What does it say? Before you start with any question, make sure that you always write the information that is given, and of course point out the things that is missing. Then of course you have, or you will have an idea what are the information or what is basically or what method you can try or do or use so that you can get into the answer. So here's what we have. It says a source of frequency of 100 hertz, 100 pi hertz, that is basically the frequency of the source, and effective potential difference, basically that is the voltage of the circuit, by the way, where you can say the AC, the source, but don't forget this is effective, yeah, it's not the maximum. It is connected across a capacitor of capacitance, so we have the value of the capacitance here, which is 200 microfarad. Don't forget, micro is 10 to the power negative 6. Calculate the capacitive impedance, XC here, of the capacitor, and the effective current of the circuit, and the maximum charge accumulated across the capacitor. So let's solve this together and see how it is done, okay? Like I said, always remember to write what is given and what is unknown. Then of course you will have an idea to or how to answer these sort of questions. So how about we write the information that is given real quick, and then of course we will move forward afterwards. Okay, it says, so we have the frequency, which is, what is the frequency here? The frequency says 100, that is obviously pi hertz, okay? And then the next thing that we have, it is the V effective, that is the, you can say the voltage source, which is 200 volts, 200 volts, okay? And then across a capacitor, so the value for the capacitor is basically 200 microfarad. How about if I just, instead of micro, I'll just go ahead with 10 to the power negative 6 farad. Okay, and then calculate the capacitive impedance, so calculate XC, that is unknown here. And then of course after that, the effective current, we can say I effective current. Okay, I effective, that is also unknown, and of course the maximum charge as well. So find Q, but not just Q, normal Q, we have to find maximum Q here. So let's start with the first one here. How do we find XC, guys? Listen, as long as they're asking you to find XC, one of the easiest way to see is using Ohm's law, yeah? And of course we will say XC is equal to what? Equal to, we can say V effective over, can we use this one here? V effective over I effective. That is one of the methods that we have. I do have V effective, but do I have the current at this point? The answer is no. So what is another way to solve this one here? And of course, in this case, we can use this one here. The second, or you can say the other equation for, let's say the inductive capacity, or you can say capacitive impedance. And of course, we said it is equal to omega C. Okay. So, but do I have omega? not directly, but I have the frequency. So instead of this one, of course, I have 1 over 2 pi, that is omega, 2 pi f multiplied by the value for the capacitance of the capacitor here. So of course now, once again, we'll just plug in the numbers now. So we'll say 2 pi multiplied by the frequency is basically 100 pi, obviously, and then multiplied by the value of the capacitor, or the capacitance of the capacitor, which is basically 200 times 10 to the power negative 6 farad. So you do the math, of course, these will cancel out. So we have 200 times 200, that is 400, you can say 4,000, you can say. And of course, multiplied by this, that is almost about 10 to the power negative something like this. All right, let's get a calculator, or maybe something faster than that. We'll just go ahead and take a look at the answer. So you can see that the value for this is basically equals to 25 ohms here. So we can say XC is equal to, XC equals to what? XC equals to 25 ohms here. That is, you found XC now. That is as simple as this. That is the first requirement. It is done. Now the second requirement is find effective current. Now, once again, you can now use the Ohm's law. Yeah? Of course, we'll say XC, which is the same as resistance, which is obviously V effective over I effective, yeah? So we want I effective here. So I effective now, by the way, since I have the inductive, or the capacitive impedance, and I have the V effective, I can easily find I effective, that is the current through the circuit here. So that is basically V effective over XC. Once again, V effective was, or the 200 volt, and then this one was 25, yeah? And of course that is equal to 8, okay? That is going to be 8 what? 8 amperes here. Okay, that is the third requirement. The fourth one here says find maximum charge here. And of course we did have this equation for the charge, yeah? We said the value for the, or capacitance of the capacitor equals to what? Equals to Q over what? Q over V here. But listen, since it says find the maximum charge here, so I'll have to make this one maximum as well. But here's the question. Do I have maximum voltage? The answer is no. So how can I find maximum voltage? Well, easy, yeah? We've already learned that. Let's say V max, let's say, if I do it in one step, equals to what? Equals to V effective times the square root of 2, you can say, yeah? So we have 200 times the square root of 2. That is basically, we'll say that is going to be V max in here, yeah? Okay, and then the value for the capacitance is also given as well. So going back to this, maximum charge in here, M for max now, of course, is equal to the C times V, but don't forget that is maximum here. So the value for the capacitance is 200 times 10 to the power negative 6, because it was microfarad, don't forget, and then multiplied by, we can say, 200 times the square root of 2 here. And then you do the math, of course, you'll find the maximum charge that is basically stored on the 2 plates of the capacitor. But don't forget, charge is measured in coulomb, so this much coulomb here. Okay, so what is going to be the value for this? And of course is equal to 0.057 coulomb here. Okay, moving on to the next one here, that is obviously, where you can see pretty easy. So let's calculate the capacitive impedance XC here. Okay, so we want to find XC. All right, says the capacitor of a capacitor of capacitance, we have 2 microfarad, that is 2 times 10 to the power negative 6 farad, and then connected across the source of frequency of 100 hertz. So you have frequency, you have the capacitance of capacitor, then of course you can easily find this. So you just, that is just the application of the equation. You plug in the numbers, and then of course you can do that. Yeah, this is the frequency, this is the value for the, or C. Then plug in the numbers, of course you'll find the answer. Easy enough. Okay, now this is also very easy enough, but let me just tell you the idea about this one. It says a source of instantaneous potential, yeah? So we have voltage equals to 10 sine 100 pi t. Whenever you're given the instantaneous values, there are something you really have to be careful with. The value that is given here, it is basically maximum here. So whether if it is voltage or current, an instantaneous voltage or instantaneous current equation, this is represents the maximum. So this is V max, okay, and of course this one, 100 pi, that is basically omega. So of course we can use this to find whatever that is unknown, or at least to help find some of the factors that are required so that we can find other, let's say, variables. Okay, so it is connected across a capacitor of capacitance. So we have C, which is 1 microfarad. Again, 1 times 10 to the power negative 6. Calculate the maximum value of the current and the phase difference between the current and the potential difference as well. So once again, how do we do this one? Let me try this one as well. So we're been asked to find the says what? Find the maximum, calculate the maximum value for the current. Yeah. So how do we do that? Take a look. This is voltage. Yeah. One of the ways to, whenever they're asking you to find the current, it is more likely you're going to need or to use the Ohm's law. Yeah. So in this case, of course, since it is a capacitance, we'll say XC is equal to V effective of what? We can say I effective. Yeah. And if we have, let's say, of course, we can use V maximum over I maximum, but don't forget, they want what? They want the current or the maximum value for the current. So easy enough, we can just use one of these. If we have, then of course we can just simply substitute in here. But I do have the V maximum, correct? But do I have I maximum? No, so I cannot use this one here. Let's say to find this one. And of course, they're asking for I maximum. So I don't have to, let's say, I don't have XC as well. So once I have XC, then I can find I maximum here. So I maximum here, you can say. So let's erase this part just for now because we don't need this part now since it is about I maximum. So we'll say that is V maximum. Okay, V maximum over I maximum here. And of course, I maximum equals to V maximum over XC. But here's a question. Do I have XC? The answer is no. But can I find XC? The answer is yes. So we'll say XC is equal to what? Equal to 1 over omega C. Very good. So now 1 over omega is equal to 2 pi f and then multiplied. As a matter of fact, we don't have to say 2 pi f because we have omega there. So the omega is basically 100 pi and then multiplied by the value of the capacitor, which is basically 1 times 10 to the power negative 6 farad. You find the answer in this. That is basically XC equal to this much, whatever that is basically in ohms. Yeah. Once you have this, you have, let's say 10, that is because it's V maximum, divided by whatever is this value, plug it into the equation, of course, you'll find I maximum, that is basically, or I maximum, let's just say, I maximum here. That is, of course, is going to be in amperes, and that's it. Now, what about the second part of the question here? It says, the phase difference between the current and the potential difference. We've learned that when we are, or when a capacitor is connected to a circuit, let's say, a pure capacitor, let's say, of course, in that case, the current leads the voltage by 90 degrees. So we can either say, but let me tell you something else here, because this is the equation or instantaneous equation for the voltage here. It doesn't say, watch this, it doesn't say minus, let's say, pi over 2, yeah? If it doesn't say this, that means this one has to be, or we can say the current in this case is leading, yeah? So let me tell you what do I mean by this. We have, or we can say, these are the instantaneous equation, yeah? If it is for current, let's say IC, whatever the value is that is maximum, of course, is going to be sine omega, which is 100 omega t, let's say, then plus, I'll have to say plus pi over 2. Why plus pi over 2? Because it's not mentioned this one that, for example, negative or minus this, yeah? So if this one, or if it doesn't mention pi over 2 or negative minus pi over 2, then I'll have to say the current is leading, because we've learned that in a, let's say, in a pure capacitor circuit, the current leads the voltage by pi over 2. So if it is not mentioned here that it is lagging behind the current, so you'll have to say the current is leading by 90 over 2. So that is the answer. Or going back to the last part of this question, what would be the phase difference? We'll say, the phase difference between the two, we'll say the current leads the voltage by either 90 degrees, or you can say by pi over 2 radians. Okay, and of course you can see that it is written here as well. Okay. Now, remember, these password questions, these are very important, and I would really recommend you solving all this. First one says, in a capacitive impedance, current leads the potential difference by what? So the current leads the potential difference, we can say by 90 degrees. Yeah? If pi over 2 were given, we could have also chose that too, yeah? But since only angles in degree are given, so of course the current leads the potential difference by just 90 degrees here. Now, XC capacitive impedance is equal to what? We've learned that XC is equal to, obviously equals to 1 over omega C, yeah? But if you don't see omega C, of course, you can break it down to 2 pi F and then C here. And of course, this one is going to be option B here in this case. And this is also very recent, as you can see here. Instead of telling you XC here, they gave you omega C here. And how do we get omega C? So from the previous equation or from the above equation, as you can see here, let's clean the board. So we have this. Zoom out this a bit. Okay, now watch this. We've said that XC is equal to what? Equal to 1 over omega C here. But if I have omega C there, if I swap their places here, you can say, of course, omega C is equal to 1 over XC here. So, of course, you can see XC. Where's XC in here? And, of course, that is this one here. So the correct option here is going to be option B here. Okay, take a look at this one here, or these three questions here. It says, the capacitance of a capacitor is this much. The maximum potential difference of the two ends is this much. That is basically, you can say, the voltage across the capacitor. The maximum value of the charge stored is equal to what? We've said that, okay, that Q equals to what? Q equals to capacitor, not this one here, sorry. Okay, we said that the capacitance of the capacitor equal to Q over what? Q over V here, correct? Yes, if that is the case, they want the maximum value. If that is the maximum value, so Q has to be maximum, this has to be maximum. So we can say maximum charge equals to the value for the capacitance of the capacitor multiplied by V max. You do the math, of course, you will find the answer. And you have this, it says maximum potential difference is this much. So you just multiply the two, you get maximum charge stored on the two plates. Okay, and then for question 5 says, in an AC circuit, or in an AC circuit, of course, which of the following is inversely proportional to the frequency of the voltage? XC, XL, or R, or all of them, yeah? And of course, it is XC, because why XC? Because we said XC is equal to, let's write this one again. Watch this one here. The XC, we said XC equal to 1 over omega C, yeah? But instead of omega C, I'll just write 2 pi FC, yeah? So you can see here, these two are inversely proportional. So of course, the answer is going to be C here, A here, okay, XC. What about B here? For B, we said, of course, so this is the correct one, which is A, basically. B, of course, it is inductive impedance, yeah? And of course, we said XL equal to omega L, or you can say 2 pi FL. So you can see that these two are directly proportional to one another, not inversely. And of course, resistance is not depend, or it does not depend on the frequency here, yeah? So it does not depend on the frequency here, or you could just take the frequency away. So if that is not true for this one, or neither this one, so it cannot be all of them. Just remember that these two depend on the frequency, okay? And of course, we can say only this one is inversely, while this one is directly. So the final answer, of course, it is A. Okay, now, for question 6 here, of course, we have this one too. This is a capacitive capacitance impedance, that is XC, which is 25. It is basically connect across AC source of frequency this much. What is the capacitance of the capacitor? That is easy enough, yeah? I'll show you the equation, or write the equation that you need to know. Then, of course, I'll leave the math on you. Okay, so once again, we'll set XC is equal to 1 over omega C, yeah? So, of course, we have frequency, so let's just go with 2 pi FC here. The question is about what is the capacitance of the capacitor. You can just swap this to here. Why or how do I get this? You can use cross multiplication. Of course, you get this one here. So the capacitance of the capacitor is equal to 1 over 2 pi F, and of course, multiplied by XC. You do the math, of course, you will get the answer. Okay, now the next point here is, so far we've been talking about the application of Ohm's law. We talked about, let's say, if let's say a resistance wholly connected to a circuit, and of course that we said, let's say a pure resistor, that is what we called it. And then after that, we said if it is a pure inductor, self-inductance connected to the circuit. And then after that, we ended up with a pure capacitance connected to the AC circuit. Yeah? But now, this time, we're going to connect all these three together and see what happens, or to the phase difference between the voltage and the current, and of course, what are the equations that we use and all that. Yeah. But before we begin, just remember this: since these are all connected in series circuit. You've studied series circuit in grade 11. When we say series circuit, that means all the devices are connected one after another, and of course there is only one loop here. So what will you notice, by the way? So of course, since it is series, so we only need one ammeter because the current through the circuit at any point will be the same throughout the circuit here. So of course, we will have a voltage across the resistance. We will have, let's say, a voltage across, let's say, the inductance here, and of course the capacitance as well. And then of course we can have a voltage, let's say, across the end of this two, for let's say the capacitor and the inductance as well, because in one of them the voltage leads the current by 90, in the other one the voltage lags by 90. So of course it is pretty interesting. So how about we go, let's say, and talk about these. Okay, let me just go through this one and tell you how it is. So this is basically the circuit that we have. So we have an alternating current. Let's start with the circuit. So here's an alternating current. You can say source. And of course, we have, let's say, a capacitance. And then, of course, let's say these two places are equal. We have an inductor, or an inductance, you can say. And of course, after that, we have a resistor as well here. And of course, all this, you can see that connected to the circuit. And of course, let's say there's an ammeter that measures the current here, and we can have a voltmeter across each one of these components here. So there's this one here, there is this one here as well. And of course, later on, you'll see that we can have a voltage across these two together here, like both together as well. So we can call this one VR. You do know that. We can call this one VL. We can call this one VC. And of course, this one is basically going to be VLC here. Okay, now, what are the properties of the current and voltage here? So we do know that we can say the current, or the total current, is the same as the current that is basically flowing through the resistor and the inductance and all that. Yeah? So we can say I total is the same as the current through the resistor, is the same as, let's say, the current through the inductance here, that is L, and of course the same as IC as well. Yeah. So because it is series circuit, so the current everywhere is basically the same thing here. What about for the voltage here? And of course, for the voltage here, of course, if we're going to find V total is additive. We'll have to use Pythagorean theorem, of course. Okay, and of course it becomes what? It becomes VR squared plus, of course, VL minus VC. But remember, this thing, or the whole inside a bracket, and both of them, where you can see the whole thing is squared here. Okay, so, and I'll tell you why this in a second. Just remember this. That is one way, let's say, how to find V total. There's another way to find V total, yes? And of course, V total we can say equal to I total, okay? And then I total, and then times the total resistance. That is Ohm's law, basically, yeah? But remember, we said I total, or the current, is the same everywhere, so I really don't have to write, or I don't need to, let's say, write I total, because I is the same everywhere in the circuit. But still, what about the Z here? What does this Z represent? Z represents the total resistance of the circuit here. So of course we call it the impedance of the circuit, yeah? So when we add or combine all the resistances here, that is basically resistance, that is basically XL and XC all together, then of course we get the total resistance of the circuit, or simply just the impedance of the circuit. So how do we do that? For this one here, of course, we'll say Z equal to, like, how do we find Z basically, yeah? We'll say, again, the square root of, we can say XR squared, don't forget, plus, and of course we can say XL minus XC, and of course close bracket square, and then all this under the square root of this. This is how we can find like each one of these values, by the way, okay? So don't forget, and also don't forget this, yeah? Remember, we have, or the voltage over this, if I want to find the voltages here, we're going to use the equations like across each component, we're going to use the equations that we've learned before. So if I want to find the V or the voltage over the resistor here, I'll say VR equals to current, because the current is the same everywhere, times the resistance. If I want to find V, let's say L, of course, that is basically current, we can say, multiply by XL, okay? And of course, if I want to find VC, of course, that is basically current times XC here as well. Now let's talk about this. Why do we use, for example, VR squared, and then these two are subtracted, and then both of them are squared? Now, for this one here, we've learned before that, okay, let's talk about the phase angle difference between all of this. Yeah, let's say, excuse me. So we have, let's say, we've talked about, let's say, this is assuming that this is VR, the voltage over. Let's take each component at a time. Yeah, the voltage and the current over the resistor. Yeah. Okay. So we said. For a resistor, both the current and the voltage are the same, yeah? So of course, this is the voltage, let's say, and this would be the current as well. But since we said the current is the same for all the components here, so IR is the same as, let's say, IL, which is the same as IC here as well, yeah? And of course, you can call it I total if you want to as well. Okay, on the other side, you can say, when we consider, let's say, the phase angle difference between the current and the voltage, for the inductor here, we said that VL, of course, VL would be leading the current IL for this inductor, let's say, or the for the inductance. Okay, so we said that the voltage would be leading the current here by 90 degrees, or we could just say pi over 2 positive. Yeah, very, very good. But and then what about the voltage across the capacitor? We said the voltage there, it's lagging behind the current. So if we take this one here, the current, let's say, the current and the voltage for the capacitance, let's say this is VC, we said it is lagging by pi over 2 here, or you can say 90 degrees if you want to as well, okay? And this is basically negative 90 as well. Okay, so, but here's the thing, yeah? We've learned that in grade 11, when we have two vectors, let's say, that are, let's say, on the same line or parallel, but in opposite direction, of course, what do? We subtract them here. So let's say this is bigger and make this one a bit smaller just for the sake of this, by the way. And the reason why smaller, because the bigger this, remember, it depends on the frequency of the source. Yeah. So the higher the frequency, this value gets bigger, this value gets smaller and smaller. So the bigger this gets, the smaller this one gets. And of course, vice versa. Yeah. The lower the frequency of the source, this gets bigger, and this one gets smaller, just in case, remember that. Okay, but we do know that, okay, by the way, the phase angle difference between VL and VC is basically this, is 180 degrees in here. Don't forget this one here. So you might be asked a question, what is the phase angle difference between the current and the voltage, let's say, across the inductance? That is obviously 90 degrees. The phase angle difference between the current and let's say the voltage across the resistor, it is 0. The phase angle difference for the current and the voltage across the capacitor, remember this, that is basically negative 90, or you can say negative pi over 2, meaning that the voltage lags behind the current, or you can say the current leads the voltage, makes no difference here. But if you want to find the phase angle difference between the voltage and the current, let's say for the capacitance, let's say the voltage is actually between the two, the voltage over the inductance here and the voltage over the capacitance here, you can see that the phase angle difference between the two is 180. If I write it this way, this angle, you can see it is a 180 degrees here. But how do we add or combine these values here? So one of them is upward, the other one is downward. So of course we're going to subtract them here. So now if you do the subtraction, obviously, just assuming that this is bigger, let's say, so of course we'll say VL minus VC. Of course you'll get a vector something like this, yeah, because they will cancel each other, or this one will be cancelled partially, and this is kind of like eliminated from the equation. Now we will be left with something like this. So this is VR, don't forget, and this is now is basically VL minus VC in here. But you do know that. How are you going to combine two values that are perpendicular to one another? Again, Pythagorean theorem here. So of course we're going to move this one to the other side here. So this is what it becomes. So the final answer to this, or not the final answer, we can say the total is going to be this one here. So we'll say this is basically represents the V total. What do I mean by V total? Now remember this. So when I say this, remember this is just the total voltage, yeah? So once you find the total, that is the total, let's say, and of course this is the angle. We're going to talk about that equation for the angle as well. Let's just say it is 30 degrees, yeah? Now you'll have to take this total back to and compare it with the current as well. So you can say if this is the current here, and let's say this is the current, and this is the V total here, and of course this is the angle between the two. So if it is positive, that means the voltage leads the current. If it is negative, of course, it is going to be in the opposite direction here. That means the current is leading the voltage by this much degrees here. So far, this is where it comes from, by the way. Okay, so this is the equation. Now there is one more thing here, which is basically for like how do we find this final angle here? Of course, for the final angle or for the angle phase difference, we'll say theta equals to tan inverse, don't forget. Now, we can use two equations here. We can either use voltage or we can use the resistance. But how do we do that? We can either say VL minus VC, of course, divided by what? Divided by VR. Where do we get this from? We get this one from this, yeah? Obviously, this is VL minus VC, and of course, this is VR, yeah? So obviously, tan theta, that is opposite over adjacent, you can say. If we don't have V voltage values, we can use this equation. We can say tan or theta equals to tan inverse of, that is XL minus XC over the resistance as well. So whichever the values that you have, you can always use this. But before we continue, there's something else I really want to know here, and that is this. Let's say we have a circuit that is has only two components in this case. Yeah, let's say it doesn't have a capacitor. So you're going to use the same equation, but if you don't have a capacitor, you're going to extract or eliminate this from the equation. So you don't have to write this one here. That is for one of them, yeah? And of course, in this case, you will not have this one either. And then as for the angle here, or let's say the resistance first, where's the equation there? Of course, you will not have this one as well. That is this, yeah? And then for the angle here, of course, you're just going to write VL over VR, or just basically XL over the resistance here. But I really want you to be careful here because let's take back all this. What if we don't have, let's say, the inductance here? Okay, if you don't have the inductance, so basically you will not have VL. That's one thing, and then you will not have XL here. That is true. You can say. As for this one, you have to be really careful here because once you take this one here, don't forget to keep the negative here, because in this case, if you take away this one here or eliminate it from the equation, then you will be left with negative VC. Or here, you'll be left with negative XC here, because this negative indicates, or perhaps you're going to get a negative angle, which means that the voltage is lagging behind the current. So it's really careful. You have to be really careful to see which one is given and which one is not given. So this is basically everything you need regarding this, yeah? And then there's one more thing, let me not forget, okay? Now for these values here, when we say V total, you can either use all maximum values here, for each one of these values here, or you can use the effective values here, yeah? Because we're dealing with let's say effective values most, so of course we're going to substitute all this, or you can say we're mostly using effective values here. So if you see me writing these values without writing, let me just take out these crosses so that it doesn't confuse you here. Okay. So like I said here, we either use maximum values or we will use effective values for all of them. Just like we've done it for the resistance, for a pure resistor, let's say, or the capacitor, let's say the capacitive impedance XC or XL, yeah? You're going to use like the maximum values, or you're going to use effective values, or you could have used the instantaneous values as well. But like I said, because we're dealing with effective values most, of course, we will use effective values in each one of these equations here, or for each one of these values, okay? So when you see me writing this equation without writing effective or maximum, just know that we are basically talking about V effective values. So if I have V effective, can I convert it to V maximum? Yes, because we've learned about that, yeah? If I have effective, we'll say, if I want to find V maximum, for example, we'll say V maximum equals to V effective times the square root of 2, okay? That is, you could do the same thing with the current, let's say, if you had current as well, yeah? I mean, but that's different here. Basically, all the currents are the same, but if you ever wanted to find, let's say, the maximum value here. So these are the equations. We've learned about all this, okay? And these are all the equations that we have. Don't forget them. And of course, knowing all this would be fair enough. Okay, so we have some study tips regarding the what we have, or what I just told you about these series circuit, let's say series circuits. One of the things it says in self-inductance, remember this, we've said it that in self-inductance, the voltage leads the current by 90, but in capacitive circuit, of course, or in the capacitive, the current leads by 90. So remember this: the phase difference between the voltage across the inductor here, the inductance, okay, or self-inductance, and the voltage over the capacitance. The phase angle difference between the two is 180, or you can say the voltage across the inductive impedance and capacitive impedance, that is also 180. So remember, the angle between the two, or phase angle difference between the two, is 180. Okay, so in a series circuit, remember this: we said if one of the values were not given or required, let's say, then of course we'll write the equation without the one or that variable that is neither required nor given. Okay, so of course, let's just say if the value for L, XL, or VL, let's say these are not given and nor required, then of course the equation that is left will be V squared R, okay, and then plus let's say VC, that is squared. You might say, Mr., but it wasn't, let's say, negative this. I would say yes, of course. Let's say V total, of course, we can say that is basically VR plus, we said, VL minus VC squared, yeah? So remember this: if you take out this part from the equation, it becomes negative VC. Negative VC, but remember, this is squared, so negative VC squared, you still get a positive value, so that is why we write positive here. The same thing for the impedance, that is the total resistance, but I want you to be careful here when it comes to finding the angle. Tan theta equals to negative VC, or you can say theta equal to tan inverse of negative VC. Why? Because once you, here's what we have, yeah? So we said obviously this one equals to VL minus VC over the resistance. So if you're taking away this one, then of course we are left with this negative, which is crucial for this, for the values. Otherwise you might get a positive value, which makes your calculation to be incorrect. Okay, or at least let's say your answer incorrect, not your calculation. Your calculation too, actually. Okay, so we'll either go with VC over VR or XC over the resistance here. So we'll do the same thing if the capacitance values were not given. Let's say the capacitor, VC, XC, and all that. If it is not given, we'll just take out or eliminate it from the equation. Then we'll just do the math on that side. Watch this. There's something also very important regarding the phase angle difference. We said if tan theta is positive, or if, because we had this one here in the equation as well, yeah? Let me just go through this one as well one more time here. So remember this. We said that if, okay? So let's write it down. Watch this. This is the main equation that we had. We said tan theta, or let's just say theta equals 2, yeah? It will be better. So theta equals to tan inverse of, okay? Of course, we said XL minus XC, and then divided by R, yeah? So of course, if XL is bigger than XC, this value, or tan, of course, tan theta, or the theta, is going to be a positive value. So what we get is basically we're going to get something like this. If this is the V total and this would be the current here, and you can see that, what does it mean if we get a positive value? That means obviously the voltage is leading the current by this many degrees or this much degrees. Okay, and then, but what if we, let's say, so it's the same thing if it is VL bigger than, let's say VC, that is the same thing, yeah? But what if it is the opposite, let's say? Okay, if we say, let's say, V this time, let's say V or XC is bigger than XL here, then, or let's say VC is bigger than VL in here. So if that is the case, if this one is bigger than this, once you're subtracting this, of course you get a negative value, or theta becomes a negative value. A negative value, that means something here, which if that is the case, this would be the total voltage, V total, and this is current. In another way, if you get a negative value, that means the voltage lags behind the current by this many degrees, you can say, or by this much degrees. Okay, so just remember this. This is also very important. And also, circuits cannot be without a resistance, so this is also something very important. Now let's solve this question. Obviously, solving this question will help you to understand how things are done here, so perhaps it makes it very easy for you. So let's go through it together and see how we can solve questions, or any question that is related to these concepts here. So this is the circuit that I have basically. I can redraw this one, or I can perhaps we can just hide it for now. Okay, so that is basically this. So what are the requirements, or what are the things that are given? I've had the things that are given. So let's move this one down a bit. Okay, so these are the things that are given, and these are obviously, it tells you based on the graph that is given, these values are given, as you can see here. So what are the things that we have? It says, find the readings of the shown ammeters and voltmeters and the phase difference between VR and V total. You can say if V total effective, watch this, V total effective is 30. When we say V total effective, that is the voltage supplied by the source, you can say. And then we have XL, we have, which is 14 ohm, we have XC, that is 5 ohm, we have the resistance, which is 12 ohms, and of course a frequency of 50 hertz as well. So the first part of the question says, find the effective current. How do we find the effective current? Now, I really want you to be careful here. We said whenever they're asking you for current, obviously you need to use Ohm's law, yeah? So of course, but remember, okay, V effective, that is the same as, because, or not V effective, I effective, that is the current through the circuit, it is shear circuit, so the current is the same everywhere, which is the same as if you say I total current through the circuit. So if that is the case, I'll say V effective total equals to what? Equals to I effective, that is obviously total, then multiplied by the total resistance here. So I effective, I think I'm writing it too big. Let's just minimize this and save some space perhaps. Okay, so once again, V effective total, okay, equals to I effective. Obviously that is the total, and then multiplied by Z, which is the total impedance here. So we'll say I effective equals to V effective total, okay, or V total, let's say effective, of course, divided by what? Divided by the total impedance. But here's a question, do I have the total impedance? The answer is no. Can I find the total impedance? The answer is yes. So how do we find the total impedance? We'll say total impedance equal to R squared plus, remember this, XL minus XC, and then of course the whole thing squared here. So now let's plug in the numbers here. Once you do this, so we have XL, where's or resistance first. Let's get rid of R is basically 12, so let's say 12 squared plus, and then XL, where's XL? That is obviously 14. Okay, minus XC is 5 in here. So now here's the square. I hope you can see the square as well. Let's make it in red so that you can see this. Okay, so now you do the math, of course, you will find the answer here. Okay, let's go back to, okay, blue. So let's just go back one step. All right, so here's going to be the value for the resistance here. Now, you do the math, use a calculator, you get this one here. But of course, we're going to have a shortcut here. Let's say the value for this one, obviously, you can see that it is basically 15 ohms. That is the total. You can set the total resistance, yeah? So if this is basically was 15, yeah? Okay, so 15 ohms. Now, the next thing now, you just have to plug in this there, yeah? So obviously it is going to be V total is 30, divide by 15, that is going to be 2 amperes. That is the first part, yeah? Now, for the second part here, what is the second part? Find the voltage, let's say, or effective voltage across the resistance. Now, here you have to use Ohm's law. So, of course, V, let's say R, we can say, VR effective equals to I effective times the resistance. I effective is obviously 2, the resistance is, it is 12, so we can say this is 24, yeah? 2 times 12, that is 24 voltage across the, we can say across the resistance here. And then the next one here, we have V across, let's say, the inductance here. Once again, that is current times XL, don't forget, okay? So the current was 2 ampere multiplied by XL was 14, yes? So 2 times 14, that is basically 28. Don't forget, that is the voltage here. Okay, next we have, it says find VC, right? The voltage across the capacitor. These are all effective, by the way. So I times XC, which is basically the current is 2 times the XC is 5, so it's going to be 10 volt, you can see here. Okay, so 10 volt in here. Now, the next thing says find VLC here. Now, if I want to do this one here, or find the voltage between the two, by the way, in one of them the voltage leads, the other one voltage lags here. We said the phase angle difference between the two is 180, yeah? So, of course, I'll have to use this one here. I'll say, by the way, we could just do this one, yeah? Because, okay, how about, because we're trying to find, let's say, the voltage you can say across, or let's just say VLC, of course, because in one of them the voltage leads, the other one the voltage lag, of course, we could just subtract between the two, correct? So in this case, of course, I'll say VLC in here, of course. What are the values that I have in here? So this is obviously 28, and then the other one is 10 here, so I'll say 28 minus 10, and of course I'll get 18 volt. That is one way that I can say. And the reason why, because in one of them the voltage leads, the other one the voltage lags, so this is what you can do here. Okay, so the last thing I forgot, I almost forgot, it says the delta theta. Okay, I think it was too fast here. So the last thing here, didn't notice this one here, the theta here. Now for the theta you can of course use different ways or different methods. One of them, we can either use the voltage or we can use the resistance here, like VL minus VC over the VR, or we can use XL minus XC over the resistance here. But I'll just use this one, tan inverse of, let's say, VL minus VC divided by VR in here. So tan inverse of, what is, we've already found VL minus VC, and that is obviously, you can see that it is 10, yeah? Was it? No, my bad. That is 18 basically divided by VR, which was 24, yeah? So of course you get a positive value, whatever the angle is. So we'll say theta is basically, or the voltage is leading by this many degrees the current, yeah? So the voltage is leading the current by this many degrees. What would have happened if VC were bigger than VL? Then of course you would have gotten a negative value. This negative value represents that the current is lagging behind the voltage. I mean, my bad, the current is leading the voltage by this many degrees. Okay, so that is basically it for this question. Inshallah, next time we'll continue from this question on practice, and we'll move forward. You'll see that solving other questions, provided enough information, will be very easy, inshallah. Till then, keep practicing, and I'll see you soon.